Okay, welcome back to another video on Minitab. In this video, I'm going to talk you through some of the basic tests you can do in Minitab. The first test we'll look at is a test where you can compare the means or medians of two samples. So say here, for example, I've got two samples, A and B, and I've measured something. I don't know exactly what it is, but I've measured something that has these values. And I want to compare these two samples to see if there's a difference between them. Now, the most important thing about statistics is, and you'll see in a moment, that running the test in Minitab is easy. If you know what you're doing, you can run a test in Minitab in 5 seconds. No exaggeration. Okay? The tricky thing, however, is knowing what test to run for what situation. And that's where you have to refer back to, there's decision trees online, there's a table in your course materials probably, or a flow diagram that'll help you choose which test goes with which situation. Okay? So in this situation, we want to compare two samples, and we have to think to ourselves, what data are in those two samples? Are they categorical data, which fit into neat categories, discrete categories? Are they continuous data, which we've measured on a continuous scale? What kind of data are they? Now in this case, you can see the numbers cover a fairly broad range, from 12 to 36 in this case, and they can take a large range of numbers within those. So there's not like these numbers appear in categories, in discrete categories. They seem to appear across a continuous scale, a measured scale. So I would assume these data are continuous. Okay, now we know these data are continuous, so we might be able to use a test that compares two means of two samples. Okay, something like a t-test. But a t-test has certain assumptions as well. The t-test assumes that your data fit a normal distribution, so a bell-shaped curve. Now, how do we figure out if our data fit a bell-shaped curve? Well, there's two things we could do. One thing we could do is just visually assess our data to see if a histogram of the data, so how the distribution of data fits, is plotted on a graph, which numbers appear more frequently than others. We can visually assess, does that look like a bell-shaped curve? So that'll introduce us to the graphing functions of Minitab. So what we can do is we can go up to the toolbar up here and go to the graph menu, click on that, and then go down to histogram. So click on histogram, and now I can create a simple histogram or a histogram with fit. And the fit will be, for example, a normal distribution. So let's try that. Let's try one with fit. Okay? Simple because I only need one variable, so a simple histogram with a fit. So I click on this option, click OK, and then I will select the variable I want to fit. So in this case, variable number A. Okay, and this is always what happens in Minitab, by the way. Whenever you want to do something, a graph or statistical analysis, a window will open like this, and you will have to tell Minitab, what do I want to do in this window? What test do I want to run? What data do I want to use for my test, and so forth. So it's asking me, I want to do a histogram with a fit like you asked me to, but what variable should I be using for that histogram? And I want to use column number 1 that contains variable A. So in my list of variables here, you can see there's these three that are all being listed A, B, and C. Because they're number columns. They have numbers in them, so Minitab recognizes those as I can work with those. I can do a histogram of those. Now just to show you, I want to show you what happens if you have a column where you've mistakenly put some text into it that you didn't intend to. So let's just close this for a second. Let's say I've got a fourth column over here, and I've accidentally put my column label D in the top of that column. And then I want to do, I have some data in here that I might want to use for an analysis later on. Now, if I go back into my graph menu up here, you can see here, column 5 is now labeled as a text column, C5-text. If I go into my graph menu, and I want to plot a histogram, and I want to plot a histogram with a fit, as we discussed before, click OK. Can you see that column 5 is not appearing as one of the options for my histogram? And that's because Minitab thinks that's a text column. It has text in it. I can't use that for numbers. I can use that to do a histogram or to do a test, so it's not appearing. So just wanted to show that as an example of what happens if you get text into the wrong columns where you don't want it to. Okay, but we want to do a histogram for column number C1, which contains variable A. So you can either click and then select down here to move it over here, or just double click on it. You can see I double clicked on it and it appears here. This is the variable I want to graph, variable a. Okay. Now it has a whole bunch of different options I can do here. I can add labels to my graph, a title, subtitles, footnotes, data labels, what's on the x-axis, what's on the y-axis. I can do all that in here, but just for a basic graph, just leave all the defaults the way they are and just click OK. And there we go. We get a lovely histogram. Now you can see there that red line is the bell-shaped curve, the normal distribution, and the blue bars are the frequency of my different measurements in my sample. And you can see the frequency here is one number, 25, comes up twice in my sample. All the others only come up once. So you might look at that and go like, that does not really look like a good fit for that bell-shaped curve. But we want to find out, is it statistically significantly different from that bell-shaped curve? Is that difference big enough for us to conclude these blue data are too different from this red line to be considered a fit? So how can we do that? Well, we can do an actual statistical analysis of the data to see if they fit a normal distribution. We can do that by going into the stat menu, where all the statistical tests are located, and then you want to go into basic statistics. That's where your basic analyses tools are, like, for example, a test for normal distribution. So if I go down this list, you'll see I come upon normality test, and it even has a little bell-shaped curve symbol next to it. So that's the place where I have the normality test option for me. So I click on that, and it'll open another window. Like I said, every time Minitab does a test, it will open a window for you to populate with the information it needs to run that test. So in this case, it's asking us for the variable. What variable do we want to test? Well, we just decided column number 1 that contains variable a. Click on that. I can double click it again, and it'll go into the variable slot here. So it's going to test variable a, column number 1. The other options here you can leave as a default. Again, you don't have to change those. You've got the Anderson-Darling test is a good vanilla kind of all-rounder test for normality. So we can leave all the standard options and just click OK. And this is what we get. We get another graph which has the same kind of principle. The red line is the normal distribution, but it's been out into a straight line. The graph has been stretched and molded to create a straight line. Okay? And then you can see here the blue dots are our data points. And the rule here is the closer the data points are to this red line, the better they fit, the better the fit between our data and a normal distribution. Okay? So visually, this looks pretty good. The blue dots, our data, fit the red line very well. The p-value is the one you actually want to look at, though. The p-value will tell you, is there a significant difference between the red line, the normal distribution, and the blue dots, our data. In this case, the p-value is 0.895, so the critical p-value is 0.05. So if we're above that critical p-value of 0.05, we must accept the null hypothesis of the test. And the null hypothesis in this example is there is no difference between our normal distribution and the data. So if that's our null hypothesis, and we have to accept it, we can conclude there's no difference in this case between our data and a normal distribution. Our data are normal. That's how you would express that. Okay, the data are normal. Excellent. Okay, so we can close that. You will see that in the session window, there have now appeared 2 lines of text saying we've done a histogram and we've done a probability plot of the variable a. Okay, that's what it's listing here in the session window. But because it's produced graphs for this, it doesn't actually give us the result of this. So for example, if you want to remember what the p-value of your normality test was, what you'd have to do is you'd have to go in, do that test again. Okay, all the same, just everything, keep it the same. Click OK again. And then what you could do is you could highlight the text here. Sorry, that's the p-value. You double click on this. Here we go. Hang on, that should open in a second if I click it the right way. Select item. Let's see if I can copy the text from here. No, I can't. But I can at least read off the p-value here, which is 0.895. Okay, 0.895. So what I can do is I can go into my session window and I can type in p equals 0.895. So I can make a manual record that that was the p-value I got from my normality test. Okay? You can also even write normality test. Okay? So that'll manually keep a record for the result I got there. And then I can keep going, and it'll make new entries for any tests I do after that. Okay. So now we've established column 1, variable A, fits a normal distribution. The data are normal. Let's say we want to compare that column of data to column number 2, which contains variable B. Okay? So we know already column A, or column 1 with variable A, fits a normal distribution. It has a mean. Can we compare the mean of this to the mean of this? Well, let's find out if column 2 with variable B also fits a normal distribution. How do we do that? We go back to our stat menu. We go back to our basic statistics. We go back to our normality test. And instead of selecting variable A this time around, we're going to select variable B. Double click on that. You can see it replaces that variable. It can only do one variable at a time. So now it's taken variable B. We click OK. And we get another graph with the dots around the red line. And you can see again visually this is a pretty good fit. And the p-value is 0.785. So again, much greater than the critical p-value of 0.05. So we can write that down. 0.785 equals 0.785. So that reminds us both of these data sets are normal. They fit a normal distribution. Okay? We accept the null hypothesis for both of these tests that the data are not different from a normal distribution. Excellent. So now we know that both of these columns of data are continuous data. They fit a normal distribution. So we are allowed to use what's called a parametric test on these data. Parametric tests assume that the data meet certain criteria. For example, the data are normal. So a parametric test to compare two means, A and B for example, is called a t-test. So where do we find the t-test to compare these two means? If we go into the stat menu, we can go into the basic statistics menu again, because the t-test is a very basic traditional test. We can go down here and you can see there's a 2-sample t-test right here. Click on that, and it asks us, again it opens a window like with any other test where Minitab is asking us to tell it what to do. And it says here both samples are in one column. Now you have to think to yourself, is that true? This would be the case if you had your data stacked into one column, and we'll see what that looks like in a moment. But at the moment, let's look at my data. My data are in 2 different columns, column 1 and column 2. So no, both samples are not in the same column, so I'll have to change this to go each sample is in its own column. Okay, I've got one column for variable A, one column for variable B, so I have to have a separate column for each. Once I've set that, you'll see there appear 2 boxes here, sample 1 and sample 2, that Minitab is asking me to fill. What samples do you want to test? So I click into one of those, and my columns with data appear. You will notice again, column number 5 with the text in it is not appearing, because I have this text up here in the white cell. So only the columns that are not considered a text column will appear here as an option. Okay, so now I want to take column A, column 1, variable A, and column 2 with variable B. So just double click on those, one after the other, and it'll fill these 2 fields in. You don't have to worry about the options. Again, the default test will work just fine. So that's as simple as it is. Tell Minitab how your data are arranged, select the 2 samples you want to test, click OK. That's it. And you can see here in my session window, I've now got, let's move this down a little bit, and let's open this up a little bit. I've got an entry here that says 2-sample t-test for variables A and B. And beneath it, you'll see there the test results for a 2-sample t-test, A versus B. It gives me the means of the 2 samples. It gives me the n, the size of each sample, 7 measurements for each. It tells me the standard deviation, the standard error, and then down here, this is the critical line. It gives me the t-test of difference, where it says the t-value is 0, the p-value is 1, and the degrees of freedom are 7. So what does that mean? It means that the p-value is 1. The critical p-value is 0.05. If the p-value is less than 0.05, we say we reject the null hypothesis of the test, and the null hypothesis in this example, in this test, for t-test, is always there is no difference between the two means I'm comparing. So in this case, our p-value is as big as it can get, 1. It's much, much bigger than our critical p-value of 0.05, so we accept the null hypothesis. There is no difference between these two means. Does that surprise us? No, because the means are actually exactly the same, 23.43. Okay, so no surprises there. We get no significant difference between these two. That's how a t-test works in Minitab. Very straightforward. Now let's assume for a moment that these two data columns did not fit a normal distribution. Let's say, for example, one of the p-values from our probability plots here, from our normality tests, came out less than 0.005. Let's say it came out as, let's hypothesize it came out as 0.00012. Then that would be less than 0.05. We'd have to reject the null hypothesis and assume there is a difference between our data and a normal distribution. So in that case, I couldn't just use a t-test, because the t-test is a parametric test. It requires the data going into it to fit a normal distribution. So what could I do in that instance? I could use a non-parametric test. So a test that does not assume that the data are normal. And that test to compare two samples is called a Mann-Whitney U-test. So let's go into the stat menu. Let's look down here. You can see there's actually their own little menu for non-parametrics. So non-parametric tests have their own little submenu. So if we click on, or we hover over that, this submenu will appear, and you'll see there's a Mann-Whitney test here. That's the test we want to run, a Mann-Whitney test. We click on that, and it's a very simple window again. It's asking me what is the first sample you want to compare, and I say sample A in column 1. What's the second sample? Column 2, sample B. Okay? Don't worry about these other things. They're not relevant. You don't have to change those. Just click OK, and the test will run. And there, right in your session window, appears the result for the second test we've run, the Mann-Whitney U-test. Okay? So it says Mann-Whitney test A and B, and it says here, again, the N, the number of measurements we have for the two samples, the median, so the median value, it's not the mean, it's the median, because you can only calculate a mean for samples that actually fit a normal distribution. And the Mann-Whitney test assumes your data don't fit a normal distribution, so it produces a median. So here are two medians, 24 and 24. Again, they're exactly the same for the two samples. And let's look down here. Here you get the output of the Mann-Whitney U-test. And it says here, let's read this together, the test is significant at 0.8979. And it says adjusted for ties. So I'd always use the last line of the test because the adjusted for ties value is a bit more accurate. Don't worry what that means, adjusted for ties. It has to do with how the maths behind the test work. But the key language here is, and this is something that's very confusing in Minitab, is the test says the test is significant at 0.8979. So you might read that and think, oh, there's a significant difference between these two medians. Is that actually the case, though? The p-value here is 0.8979. It doesn't say it, but that's the p-value. P is 8979, 0.8979. That is much, much greater than 0.05. Okay, so we're way above the critical p-value, which means we have to accept the null hypothesis of the test. And the null hypothesis is always there is no difference between these two medians. So that means, actually, looking at the p-value, there is no difference between these two medians. Okay? So the tricky thing here is that the Mann-Whitney test in Minitab always says the test is significant at, regardless of what this p-value reports. Okay? So it's a weird use of language here in Minitab that you have to be very aware of. And for the Mann-Whitney U test, just look at the p-value to decide whether or not your test was significant or not. And in this case, it was non-significant. P was greater than 0.05. There is no difference between these two medians. And again, that shouldn't surprise us because the medians are exactly the same. Okay? So that should always double check your conclusions from a test against the actual data, against the means or the medians you're comparing, to see, does that make sense? Does it make sense that I have no difference here between these two medians if they're exactly the same? Yes, that makes perfect sense. So that is a good quality check of your interpretation. Okay, so that was a two sample test. I've got two samples to compare. What if we wanted to do a 3 sample test or a 4 sample test? What if there's more than 2 samples, more than 2 means, more than 2 medians that we want to compare? Okay, what would happen then? Well, in this example, I've got 3 means or 3 medians, A, B, and C. I've got 3 samples I can compare. So what test could I use for that? Well, if you look up, again, in your guidance or in Minitab, you will find, I should actually mention here, that there's an assistant up here. And I think I'll do a separate video on the assistant that'll help you choose your statistical analysis. Okay? But however you figure it out, you will probably come across information that tells you that for comparing 3 or more samples with each other, for example, comparing 3 or more means, you will need something called a ANOVA, for example, an analysis of variance test, ANOVA. So how does the ANOVA work? Well, if we go into, in Minitab, into the stat menu, you will see the ANOVA is such a fundamental and important test, it has its own little menu. So you will find an ANOVA menu. So if I go into the ANOVA menu, you'll see here it has a whole range of different types of ANOVAs, and the one we're most interested in at the moment is a one-way ANOVA. A one-way ANOVA is a test that works on an experiment where there's only one factor that is different between the samples. So, or one factor we've investigated. In this case, we've investigated whatever variable this is we've measured. Okay, so one factor might be, I don't know, the fertilizer treatment in a growth experiment. Okay, so we go to one-way ANOVA, and it'll open a window again, and it'll ask us, just like with the t-test, are the response data in one column, or are they in separate columns for each factor level? So the level is the treatment within that factor, like fertilizer. So A, B, and C might be three different concentrations of fertilizer. The factor we've investigated is fertilizer. The levels of the factor, in this case fertilizer, are the 3 levels, 3 concentrations, right? 1 milligram per liter, 2 milligrams per liter, 3 milligrams per liter, whatever it might be. Now again, in this example, my data are in separate columns, right? Each factor level, each concentration of fertilizer is in a separate column. So I'm going to have to select that for my analysis, okay? I've got to tell Minitab they're in a separate column for each factor level. Now you'll notice I still don't see my columns appear here in my selection window. The reason for that is very simple. I just have to click into the responses window here, and then they will appear. Because Minitab is asking me, what are the columns containing your response data? The things you measured. Well, those 3 columns are over here. I can highlight them all in one go and click select. And Minitab will put them over here. Do you see that? A to C. It's taken all 3 variables and put them into the response window. Now, we'll not concern ourselves with all these options down here again, because for the moment, all we want to do is a basic one-way ANOVA, and this setting will do that just fine. So we've got responses A to C. We can click OK, and it'll run an ANOVA. Now, the first thing it'll do is it'll produce an interval plot. Now, this interval plot means to show visually how there's potentially differences between the 3 different means. These are the 3 means. These are the errors around those means. But this is a very bad plot. Don't use a plot like this to illustrate your data, okay? It's bad for a number of reasons, primarily because it has a line connecting the 3 means, which doesn't make sense, okay? They're separate samples. They shouldn't be connected by lines. So I usually just close this and ignore it. You can always do a graph separately later on. Okay, but where is the output from our ANOVA? You can see here, if I scroll up in my session window a bit, you can see here, there's the one-way ANOVA. Okay, there's the output for the one-way ANOVA. And it's quite long. It's a pretty sophisticated analysis. So you can see here it lists the null hypothesis, that all means are equal, the alternative hypothesis, the critical p-value. It lists all those things. It tells us what the factor was and the factor levels. And then finally, it gives us the analysis of variance. And this is where you'll find your p-value. This is the important bit. So here, for example, you'll find the source of the error in this case. So the analysis of variance looking at the amount of variation in the data, and it's assigning a portion of that variation to the factor that you're investigating. And from that, it calculates a p-value. So here in this case, you can see the p-value is 0.106. 0.106. That is not significant. The p-value is above 0.05, and we have a non-significant result. Okay? So the data, the means of these three different groups are not different from each other. Now, that should be the end of our ANOVA. There's no difference between these three means. We can kind of put that one to bed. But there's a couple of things I want to mention about the ANOVA, because really I've cheated. I've done something, I've run the ANOVA without doing the necessary quality checks, right? So remember, what were the quality checks we had to do for the t-test? Well, we had to check whether the A and B variables fit a normal distribution. We never checked whether the C column also fits a normal distribution. The ANOVA is a parametric test, just like a t-test. It requests or it requires data that have a normal distribution in each of the different means I'm comparing. So we haven't checked column C3 for normality yet. So let's do that now. Check column 3, basic statistics, normality test, and let's do column 3, variable C. Click OK. Once again, we get our red line graph with the blue dots representing our data around it. And in this case, you can see the p-value is 0.420. 0.420. So I can just put in here normality test, p equals 0.420. That's lower than the other tests we did, but it's still above the critical p-value of 0.05, so we accept the null hypothesis. There is no difference between the normal distribution and our variable or our data in column C3, the C variable, so it's fine to use for the ANOVA. The ANOVA will be happy with that. But there's something else we have to do for the ANOVA that I haven't mentioned yet. The ANOVA stands for analysis of variance. So we have to check that the data for an ANOVA have equal variance. Okay? How do we check that? Well, in the stats menu, under ANOVA, you will find there is a little sub-menu here which says test for equal variances. Test for equal variances. That's an important diagnostic to run before you do an ANOVA. Now, the reason I ran the ANOVA previously without doing this test is to show you that Minitab will run a test as long as, in principle, the numbers are there for it to run the test. Minitab will run the test. Whatever you tell it to do, Minitab will do. It's your responsibility to check that the test you're using is actually suitable for those data. Okay? So in the case of a one-way ANOVA, you have to check, are the data continuous? Do they fit a normal distribution? And are the variances equal amongst the groups I'm comparing? Okay, let's click test for equal variances. Again, it's asking me, are the data in one column or are they in separate columns? Well, they're all in separate columns, so I click on that option. Click on the response box, and I select my three variables. Select all three, click OK, and it runs the test for me. Now it says here, this is interesting. Let's have a look at this box, this graph. It says here, these are the three means essentially with the variation around them. And you can see these two don't really overlap. Interesting. Let's look at the Levene's test here. So there's two boxes here, multiple comparisons and Levene's test. Levene's test is a good all-around test for equal variance, and the p-value for it is 0.058. That's just above the critical p-value of 0.05. The null hypothesis of this test is there is no differences between the variances of the different groups, and we're just about able to accept that null hypothesis. Okay, the p-value is just above 0.05, so we accept the null hypothesis. There is no differences. There's no difference in the variance between these three groups, so that matches the assumption of the one-way ANOVA. So we were right to run our one-way ANOVA. Our one-way ANOVA just about should fit the data and should work. Okay? But you see, you have to run these diagnostic tests yourselves. Minitab will not remind you of them. Minitab will not ask you for them. It'll just run whatever test you tell them to. So you have to remember to run the diagnostic tests, like test for normality, test for equal variance, before you run the actual test for differences, for example. Okay, now there's one last thing we have to discuss here. And that is, just because the data going into your ANOVA fit a normal distribution and have equal variances does not necessarily mean the ANOVA worked 100%. There's another thing we need to check, and that's actually the most important thing to check, to make sure that our one-way ANOVA worked properly. And you'll see many papers and many statisticians who will tell you, actually, the only thing that really matters is this next thing we're going to do to check if the ANOVA worked properly. So this thing we're going to do is something called, we're going to check the residuals of the ANOVA. Now, where are the residuals? Well, if I go back to run my ANOVA again, so I go back to my stats menu, go back to my ANOVA, go back to my one-way ANOVA, you'll see here we still have our responses A to C that we can run the ANOVA on again, but there's also something called storage. So down here there's a button called storage. If I click on that, I can ask the Minitab to store the residuals of my ANOVA. Do you see that here? Residuals. I tick that box, click OK, and now Minitab is going to create a new column in my spreadsheet with the residuals of the ANOVA module. I'm not going to go into what residuals actually are. You can look that up, but Minitab is going to generate them for my data. So I click OK. It's going to run the ANOVA again, like it did before. So we'll get another ANOVA output. It's going to be exactly the same as before, but you can see here how it's created 3 residual columns. Yeah? 3 residual columns for my ANOVA. So I can check those for normality, because they should be normally distributed, right, if the model fit. So I can go into Stat, Basic Statistics, Normality Test, and now instead of testing any of the original variables, I can test my residual number 1. Double click that, click OK, and the p-value is 0.895, not different from a normal distribution. That's okay. The second one is going to be basic stats, normality, residual number 2. Yeah, 0.785. You'll note that these are the exact same p-values we had when we originally tested for normality. So in this special case, when you run an ANOVA like this, the p-values for your residuals will be exactly the same as the p-values for the normality test going into the ANOVA. Okay, see 0.420. Okay, so that is a one-way ANOVA. We've now tested, is there a difference between these means? And our p-value here showed us there is no difference between these means. That should put the case closed. There's no difference between these means. However, let's run an example where there might be a difference between these means. Let's increase some of these values here for column C3 for variable C. Let's make this a bit higher. Okay, and let's see what happens then. Now let's double check, now that we've done this, that the data still have a normal distribution. Normality test. Okay. Column C3 with the variable C. Oh yeah, p-value is 0.914. That's perfectly normal. That's good. So it's still suitable for an ANOVA. And if I do the equal variance test, let's check that. I can keep the responses A to C. That's perfectly fine. I've just changed some of the numbers, obviously. Click OK. And I get a Levene's test that's a bit better than it was before, actually. I get a Levene's test p-value that is 0.069. So the data, the p-value is above 0.05. We accept the null hypothesis. There's no difference between these variances. Excellent. Okay, so my data are good to go for another ANOVA. Let's do that then. ANOVA, one way, responses A to C, just like before, and I'm going to store the residuals again, but because actually I'm not going to do that, because you've just seen that the residuals are going to be the same as the normality test going into the test, going into the ANOVA. Okay, I'm just going to do that without the residuals, and here we go. We've got a new ANOVA output, and what does it say? Oh, let's have a look here. That's my new ANOVA, right? Look here, the p-value for my ANOVA is now 0.008. 0.008. That's much less than 0.05. So that means I have a significant difference between these means. Somewhere between these three means, there's a significant difference. Now, the problem with the one-way ANOVA is I don't know where that difference lies. Is it between A and B? Is it between A and C? Or is it between B and C? I can't tell, because the ANOVA only produces one p-value for all three means being compared. So what can I do in this situation? Well, I could do what's called a post hoc test. So I could start doing, you could manually do it. You could do a t-test comparing A to B. You could do a t-test comparing A to C. You could do a t-test comparing B to C. And that way you could figure out which mean is different from which. But that's a bit laborious, and it also is prone to errors. Again, I won't go into details on that, but it creates problems. Let me put it that way. But an easy way to run a post hoc test that doesn't have those errors is to go into your ANOVA menu, go back to your one-way ANOVA, and then when you have your window open for your one-way ANOVA, click on Comparisons. And then in the Comparisons window, you can select one of several so-called post hoc procedures which are going to compare the individual means. And the common one used is Tukey's test. Tukey, will compare each mean against the other means. So we tick that one, click OK, and click OK again. You'll see it creates our interval plot again. We can get rid of that one. It creates a plot for the Tukey test, but don't worry about that. Don't look at that. Let's just go right into the output in the session window. You can see it's run a whole new ANOVA with an additional Tukey pairwise comparisons section. So here's where we can see whether or not there's differences between our individual means. Now you can see here, for each group, for each variable, C, B, and A, it's produced a mean, and it's also produced a grouping number, A, or grouping letter, A or B. And it says here, means that do not share a letter are significantly different. So let's have a look. Variable C, column C, has a grouping letter A, and B and A have a grouping letter B. So, because C does not share the same letter as A and B, it has an A that these two do not have, it's different from the other two. So the mean value of column C is significantly different from B or A. In fact, we can even say it's significantly greater than, because you can see here the mean is greater than that of those two columns. So, column C has a significantly greater mean than A or B, but A or B, they are not different from each other because they share the same letter. Okay? So fairly straightforward. Tukey's test will allow you to conclude which mean is different from which. Okay, now that was a one-way ANOVA, but what if, and let me just get rid of these residuals here, what if one or more of my variables did not have normal distribution? Or what if the variance between these different means, or the different groups, was different from each other? Okay, let's say, for example, I suddenly have a 2 in here and a 108 value. Those are two extreme values that should introduce a lot of variation into this group, right? Let's see if we still have equal variance. Let's go into the Stat menu, under ANOVA, and test for equal variances again. Okay, they're all in separate columns. Yeah, that's all good. Click OK, and look at this now. We've got a huge variance in our variable in column 3, and a very small variance in these two, because we've introduced these big outliers. But, interestingly, our Levene's test is still telling us p-value is 0.017. There's no significant difference in the variance between these groups. So we don't have unequal variance, so let's play around with the data a bit more. Let's make this a bit more extreme. Let's put in a value of 1005. Okay, boom. That's really going to throw it for a loop. Now let's see if we can test for equal variances again. Yeah. Oh, it's actually going, it's making it better. It's going up. 0.304 is our p-value now. So clearly, I might have to change some of the other data in one of the other columns as well. So let's make the variance in column A a little bit lower. Let's make that a 31. Let's make that a 35. let's make some of these 30s, 32 and 34. Let's look at what it's like next. So stat ANOVA, test for equivariances, click OK, and it's still not giving us differences, but you can kind of tell that these groups are now looking very different from each other in terms of their variances. Okay, it's not significant, but let's assume, for the purposes of this this demonstration, that we now have unequal variances, that this p-value was below 0.05 and the variance would not be the same between these three groups. In that situation, you can't really use an ANOVA because the ANOVA assumes the data have equal variance. So what could we do instead? Well, just like with the t-test, if the data didn't fit the criteria for the t-test, we were able to use a non-parametric alternative. And the same is true for these data. So there's a non-parametric alternative to an ANOVA, and that's called a Kruskal-Wallis test. You'll find it under Stat, Non-Parametrics, Kruskal-Wallis. Click on that. Here's a Kruskal-Wallis window. Now you'll note, it's asking me for two things, a response and a factor. And if I click the response window here, and the factor, like, I don't know, fill these, that doesn't really make sense because these are all responses. These are all things I've measured, right? These are all results variables that I've measured in an experiment. So Kruskal-Wallis tests in Minitab are not set up to work when the data are in separate columns like this. Okay? We will have to make this Kruskal-Wallis test work, we will have to stack all of our data into one column. So we'll have to put all the numbers into one column and put all the labels for those columns into a column next to it. You could do that manually, right? You could just copy these numbers into one column and then type the A letter into the column next to it. But there's a much easier way in Minitab of doing it, and that has to do with the stack command. You can find under Data up here in the menu, Data, Stack, Columns. Okay, so you go into Data. Let's do that again. Data, and then choose Stack, and then hover over that, and you'll have these options, and you want to stack columns. Okay, you have 3 columns you want to stack. So click on that. Which columns do you want to stack? You want to stack columns A, B, or 1, 2, and 3 with variables A, B, and C. So you can highlight all 3, click Select, and now it's asking me where do you want to store those stacked columns. Now I want to keep it nice and neat in the same worksheet I'm currently working in, so I'm going to select Column of the current worksheet. Click in the box. Which column do you want to put it in? Well, I'll put it into column 6, column C6. Okay? You can choose any empty column, column C6 for example, and then it's asking you where to put the subscripts. The subscripts are the labels that are at the heading of each column. So in this case, I want to put the subscripts in column 5, right next door. Column 5, C5. Okay? Click OK, and voila. As if by magic, it's created a new column in column 6 with all the data stacked on top of each other, and it's created a new column in column 5 that is a text column because it has text labels, but that's fine because it's not the data, it's the labels we have in this column. That's fine. Now the only thing it's missing is a name for these 2 columns. It'd be handy to have a name for them so we can find them more easily. The A column, or the column 5, is the factor, is the thing, or the factor level we should say, right? But it's the factor, the thing, the fertilizer, for example, that we've applied. And then the thing we've measured, the response, is in column 6. So I call it factor and response. Okay, and that gives us a nice label for each of those columns. And now I can go back into my Kruskal-Wallis test, non-parametrics, Kruskal-Wallis. And now you can see it's quite easy to put these data into our Kruskal-Wallis test because I have my response. It's in column 6. So I click on that, double click, and then factor. Once I click on the factor box, you can see suddenly the column 5, the text column, actually appears because it's a text column, but it's labeling our responses, so that's perfectly suitable to put into the factor column. We click OK, and we get a Kruskal-Wallis test. Here we go. In the session window is a Kruskal-Wallis test. Okay? The key thing here down here again is the p-value adjusted for ties. In this case, the p-value is 0.016. That's below the critical p-value of 0.05. That means there's a significant difference between the medians. Now again, these are medians we're comparing, not means, because the data, we assume, do not fit a normal distribution. So we've got 3 medians, 32, 24, and 38, and the p-value tells us there is probably a difference. There is a significant difference, not probably, there is a significant difference between these 3 medians. Now, just like with the one-way ANOVA, it doesn't tell us where those are, but it tells us there's a significant difference between them somewhere. Unlike with a one-way ANOVA, however, there is no easy way in Minitab to run a post-hoc test to compare the medians of each of these groups against each other, like we did with the 2-keys test in the one-way ANOVA. So in Minitab, you're kind of stuck with this result. That's the best you can do. There's ways around it, but those get quite complicated, so we'll leave it at that. That's the p-value for the overall Kruskal-Wallis test. Okay, so now we've done comparisons of 2 samples. We've now done comparisons of 3 or more samples, right? This analysis on ANOVA or Kruskal-Wallis would work just as well if we had 4, 5, 6, 7, 10 columns worth of data, right? It works for multiple groups as long as it's more than 3, and as long as it's only one factor we've investigated. Okay, in the next video, I'll show you how to do something called a 2-factor analysis, for example, a 2-way ANOVA. And then there's going to be a final video where we're going to look at some basics like, there's going to be 2 more videos, a chi-square test video and a regression and correlation video.